Today we will see design and implementation of dielectric resonator antennas for wireless communication system. In previous lecture, we have seen that why DRA, and in that question why DRA, because a lot of metallic antennas are already available worldwide. So we spoke about that efficiency of dielectric resonator antennas are higher than 95%, whereas patch antennas used to fail at higher frequency because a huge amount of loss is being offered by patch antennas. Today we will go one step ahead. Why DRA? The dielectric resonator antennas have mode control. So this feature is absolutely provide flexibility to antenna designer. Then with the help of dielectric resonator antennas, we can have bandwidth control. So total control over bandwidth is within the designer scope. Then the next point is polarization control. In DRA design, the designer has full control over polarization. The designer can choose circular polarization, he can choose LSCP, he can use RSCP, he can use linear polarization. So total control on polarization is available with the designer. One more feature that is known as beam width control. The designer of DRA have total control on beam width. He can steer the beam, he can rotate beam, he can limit beam. So beam control is there with the designer. As I already told that it has huge efficiency. Even nowadays the DRA design have even better than 95% efficiency in the design. Very crucial and very important parameter, design flexibility. Reason being, the DRA give us 3D shape, and in 3D shape we have A, B and D dimensions. Because of these three A, B, D dimensions, we can have A by B, B by D, two different aspect ratios. And generally the design parameter to have aspect ratio is between 1 and 2.5. So choosing different combination of these two aspect ratios, we can diversify our design. The mode which we want to excite will be possible by regulating this aspect ratio. It means this feature was not available to the patch designers, whereas DRA designer have total control on the resonant modes which he need to excite. Another important parameter, generally for patch designer they have FR4 and few other substrate, but in DRA we have thousands of substrate material available, and the permittivity which is dependent on frequency have 10 to 1600. It means by regulating or by controlling permittivity of the substrate, the frequency and other parameters can be crucially controlled. Miniaturization. By mode control, we can miniaturize and deminiaturize our design. Mode merging and mode shifting. Using the precise value of aspect ratio, we will be able to play with these modes. Either we can shift these modes to merge at a point, or we can split these modes to get at different points. So as I told you in the previous lecture, that the mode control will be a wonderful application in getting wider bandwidth as well as getting tuned frequency, or 3, 2, 1, whatever the frequencies or bands we require, we can split these bands at distant apart. It means by this tuning feature we can have both the things, mode merging for wide bandwidth and mode splitting for single and multiple bands. Structure is another important parameter in DRA because it has 3D. So different structures can be formulated, and the structure control will give us the beam control, gain control, polarization control. So various tuning parameters can be obtained by designing different shapes of DRA. Boundary conditions, these are important parameters. Depending on the boundary, we can develop characteristic equation, we can develop transcendental equation. In DRA, transcendental equation is important part because in characteristic equation, the formulation to achieve resonant frequency is not so accurate, but approximate results we are able to get. Whereas if we control boundary of DRA, we can get transcendental frequency. In that, electrical length is taken into account, and we can have precise resonant frequency. When we say resonant frequency, the resonant frequency formulations are different for different shapes. For rectangular DRA, the formulation used is different because Bessel functions are not being accounted for. Whereas in cylindrical DRA, we have different formulation, and this accounts the Bessel functions. The size of DRA is dependent on guided wavelength as well as permittivity of the material chosen, right from 10 epsilon r to 1600 epsilon r. So wide variety, wide diversification is available with us. Slot length of DRA is generally 0.4 lambda upon under root epsilon r. Slot width is 0.2 into length of slot. Stub length, which is used for quarter wave length, that is lambda by 4, and based on that we can devise cylindrical DRA or rectangular DRA for getting different parameters such as gain, bandwidth, resonant frequency, circular polarization, and there are many other parameters. More than 50 parameters are there. We can play with those parameters. So this is wonderful application of DRA. We can stop it here.